Okay, so this is number 5. So this is question 5. One way we're going to put it is that they determine the equation that describes the following functions. An input is 3 less than the output. So what they mean by that is, say this is our x and our y, like we're used to having. Our input, so that's our x, when we put our x in, is 3 less than the output. So an example of that could be 2 is 3 less than the number 5. Okay? But then that range could be anything. That could be 3 and 6, 7 and 10. All of those are up there, okay? So this is just an example of something it could be. So let's just start with what we got. Okay, so the input is 3 less than the output. Another way of also describing something like that is we have our y, think of that as our output, and our x is the input. So whatever we input, the output will be 3 less than it. So in other words, oh sorry, the output's 3 less. I have these backwards. Imagine it's 5 and 2, my fault. It's 3 less than the input, right? Does that make sense? Another way of describing that is x subtract 3. Whatever I put in for x, I take 3 away from it, and that will be my y. Okay? The output is 5 less. Oh, these are all separate questions. I thought this was one question. Oh, okay, so that's pretty straightforward, actually. Okay, so then for B, do you want to try B?
Sure.
Okay, give B a try yourself.
Mm-hmm.
Okay, so the next one says the output, which is our y, is 5 less than the input multiplied by 2. So our y, and here's our input is our x. Our output is 5 less, so the output is 5 less than the input multiplied by 2. Think of it like BEDMAS. I got to deal with the multiplication first. So my input is x, and I need to multiply it by 2. Okay,
Mm-hmm.
and I also, my output is 5 less than that number. So whatever that number is, I take 5 away from it, and that gives me my output. So the equation of this is y is equal to 2x minus 5.
Oh, okay.
Does that make sense?
Yeah.
So the sum of the input and the output is 5. So our input has been x, and our output has been y, right? The sum of, do you know what sum means?
The total.
Total, but what operation? Do you know what the operation is? I'm just testing something. Sum deals with addition.
Oh, okay.
Okay? So, the sum of the input and output, how would I represent that?
Okay, since it's the sum means addition, so x plus 5?
Yep, x plus y is equal to
5.
5. That's the whole question.
Oh, that's it?
Now, they may, in terms of graphing, we normally graph with y is equal to something. So we usually put everything equal to the output, in which case this would then become y is equal to 5 subtracted by x. That would be another way to represent that equation. Okay?
Because you have to isolate y.
Yeah. And now, it doesn't actually say we had to in this question, but normally when we go to do graphing, our output, we keep the y, which is our output, alone by itself on one side and the equation to the other. Okay, so Martin's building a new closet, and, you know, he's got, it's at the corner in his house. There you go. And he's going to build it like this, roughly. Okay? Now, he says that the total length of the 2 new walls, the 2 dotted ones are the new walls, because here's our closet. Okay? So these are our 2 new walls. And we know that this is, say, we're going to name this, these are the widths, and these are the lengths. Okay? Now, let's go to the last thing it says. Martin wants the length of the closet to be twice as long as the width. Okay? So that means this length from here to here is going to be 2 times as long. So if the width was, say, 5, the length would be 10. Does that make sense?
Mm-hmm.
Okay, so in other words, this operation, we can put it as an equation. The length is equal to, how would I represent the length in terms of W?
2W?
2W, yeah.
Okay.
Okay. So explain why L equals 2W. And that's where you just refer to the question.
Mm-hmm.
Okay. B. Let the function FL be the sum of the length and the width. Find the equation for FL. Okay, so the sum of the length and the width. Now, I'm not sure if they're just referring to the length and the width of the new two walls or all the walls together. I'm assuming they're just talking about this new length and this new width. So in other words, they want to put this as an equation, okay? So our B, they said let it be the sum of. So if F at L, remember we use this to represent an equation, F at L, equals, and they want it to be the sum of the length and the width. So they've spelt it out for us. That's our length plus our width. So the new length in the function, F at L, is equal to length plus width. We also discovered that, where is it? The total length of the two new walls is 12m. So as a side note, the total length, so when we add these two together, we actually know that F at L is going to be 12, length plus width. So we actually know 12 is equal to L plus W as a side note. Okay, he says that in the question. So, okay.
The back it said
So what they've done now is they've decided that they want this to be a function of L only, and that's what they mean by when they write. It's my fault. I didn't realize the two L's were corresponding to each other. This L, when they write a function of L, what they mean is they want the only variable in the question to be L. And right now we have a W in the question. So we need to substitute to do something to solve this, to take this W away, which we know we can do. In fact, we have a second equation up here. And the second equation says L is equal to 2W. Well, we need to isolate for just W, okay, so that we can replace this W with a function of L. So we're going to isolate for W. So we'll rearrange this equation. W is also equal to L what?
2.
Divided by 2 when I bring the 2 over, right? So I can substitute now. F at L is equal to L plus L over 2, okay? And now, because these are both L, we're actually going to turn this into a fraction. This is L over 1, technically, right? And to add fractions together, we need a common denominator, so that's not enough. F at L is equal to 2L over 2 plus 1L over 2. Okay, technically there's a 1 there. When we go to add these two fractions together, what do we get? 3L over 2. Is that exactly what they say in the back?
Yeah.
Yeah.
So I was wondering how they got that.
Yeah, so what they're saying is, I didn't realize the L's were drawn different, but what they're trying to say is they wanted it as a function of the only variable in the question to be L. And that's what they talk about when they have F at X. You know, when you work with F at X, the only variable in that question is X. They wanted you to rearrange it for that. What they say in C is that graph Y is equal to F at L. So in other words, this exact equation, they just want you to replace F at L with Y so that we have an output now on a graph. So there's our Y, and we have 3L over 2. So now you need to graph that, which is, it's just the slope of a straight line. It'd be relatively straightforward. Describe the desired length and width. Okay, so absolute value, essentially, the way they kind of have it set up here is you have an origin, right? And at your origin, you have the number 0. Now, 0 is technically not negative or positive. It's its own self, okay? And in absolute value, you can have 0. Then you have numbers 1, 2, 3, 4, and so on in the positive direction, and negative 1, negative 2, negative 3, and so on. Now, the whole point of absolute values, they want you to realize they want pretty much the unit amount, and we represent it as a positive number, the unit amount. So say we're at the number that represents positive 2, right? So when they give you a function of absolute value, they might tell you it looks like this. F at X, as an equation, is equal to, and this is how they represent it, 2 straight lines beside it. That means absolute value of X. So in this instance, if our input, our X, is 2, positive 2, I got to plug that into the equation. my output is also going to be positive 2. So in other words, let's say this is our A. We'll say x is 2. So I plug it into that equation. F at x equals absolute value of 2. Well, my f at x is just positive 2. Okay? And if we were to graph it, we would say y is equal to 2. That was if we're going to graph the function. We need an output, right?
Mm-hmm.
Okay. Same idea. Let's say if it's the other way, though. Let's say our negative 3, okay, is our input. Same function, b. X is equal to negative 3. When I go to plug it into this equation, f at x is equal to the absolute value of negative 3. Well, the absolute value of negative 3 is actually just positive 3. So in other words, when we go to graph it again, our y would be positive 3.
So anything that's negative will
Anything's negative is just the same value positive, okay? Now, the only special thing is, the major special thing is when you go to graph this. This graph is different. Let's put it on a new page for you. This graph, let's say, okay? So say we have 2, 4, 6. That should be 4. 4, 6, 8, 10. Okay? Same idea this way. Negative 2, 4, 6, 8, and 10. Should really save a graph with the numbers on it. Okay, so we have this graph. Say we just have this regular function, f at x is equal to the absolute value of x. Okay, when we use an input of, let's say, the number 1. So when x is 1, so that's when I go across here. When I put x as positive 1, what's y going to be? 1. So here's my point on the graph, 1 and 1. Okay, now here's the tricky one. What about when my input is 0? What is it? What's my output, my y going to be, or my f at x?
0?
0, yeah. So in that one, 0, 0, right? So that point is at 0 and 0, right?
Mm-hmm.
We know when we went to x at 1, we got 1 and 1. Mm-hmm. What about when x is positive 2? We're going to get 2 and 2. Pretty straightforward, eh?
Yeah.
That's a simple graph. So in other words, we have a diagonal line, 45 degrees, right?
Yeah.
Now, the tricky part is when we have negatives. If I have an input of negative 1, what is my output going to be?
Negative 1.
No, if
y?
it's negative 1, it's going to be positive 1, my output. Oh. So again, I'm in the positive direction. If it's negative 2, positive 2. Negative 4, positive 4. So in other words, these same values, when my x is negative, my y value is still positive. When it's negative 2, it's still 2. When we said it was negative 4, it's 4. So again, I have another diagonal straight line going 45 degrees in the other direction. Mm-hmm. So that's what this type of graph will look like. Okay? Now this graph can shift left and right, but essentially that's the idea of the absolute value. Okay. So consider these both two separate graphs. The functions that they deal with are, first of all, a linear function. A linear function is, the basic one is y equals x, but really the idea behind that one is y equals mx plus b. Mm-hmm. Remember, that's how we graph it. Yeah. The y equals x function, linear, is just literally a line that goes to there. Mm-hmm. Okay, that's the y equals x function. Another function they have is a parabola. We'll call that y equals x squared. Okay, mm-hmm. And remember that can be our a with our h and our k. Every function can technically be written that way. That's the idea behind them. This function is a parabola, so it looks like this. 1 is 1, 2 is 4, 2, 3 is 9. So we have, here we go. This is a quadratic function, it's called. Mm-hmm. Okay. And again, we can play around with graphing that one. What other ones do they do? They'll do an asymptote. I'll draw those on the next page. Asymptote is, sorry, that's too high. Essentially, an asymptote is very close to one of the intercepts. Never touches, and then at the other end, it does the exact same thing upwards, okay? And this would be reciprocal, so this is your y equals 1 over x, okay? And the same idea happens down on this side of it. So what happens is, on this asymptote, I know it's not perfectly drawn, but on this asymptote, this function doesn't exist on the y-axis or the x-axis. But again, that can shift left, right, up, down, side to side. Just like I can shift a linear, and I can shift a quadratic. So it could possibly not exist on +1 and +1 maybe, or +1 and -3. It can shift everywhere. But there'll be points where they don't exist when this reciprocal is like that. Another function they have, we just saw, is absolute value. I'll do it in like this. This would be your absolute value function. That would be written as y is equal to the absolute value of x. Okay? So the only difference between y at x and y absolute value is once it goes on the negative side, y is still positive. It always stays positive.
Okay.
Does that make sense?
Yeah.
Okay. Let's give you 2 more here. Okay. Another function that you could deal with is the square root of a number. So that actually looks like, so what they've done, now on their square root, this is a y is equal to the root of x, okay? Now, it's a little funny, they've done it only as positive.
Can't they go negative?
Yes. Technically, unless they have some type of, okay, sorry, this is y. 1, 2, 3 is 9. They want it to be a function, okay? Because this is called functions, this course. Now, technically, you're right. There's a positive and a negative to this because the square root of a number has 2 answers, a plus and a negative. But in order to be a function, it has to pass the vertical line test. And if we were to draw this part, do you remember that? Vertical line test wouldn't work, okay? So this can't be a function anymore. So we're only dealing with it when it's on the positive end of the square root, okay? Does that make sense?
Yeah.
Okay, that's why I have that one there. Another one is an exponential function. An exponential function, y equals, for example, they use the number base number 2. It could be any base number to the power of x. Okay. Now, when it's the base number 2, what happens is on to the left of the y, it's below, and then it actually hits the number. Oops, sorry, not there. It's the number 1. It'll always, exponential functions will always cross the y-axis at 1 because when x is 0, when your exponent is 0, you always know the answer is 1, right? And then after that, it takes off like this, okay? And I'm going to show you another exponential function. Let's say we had, this is still exponential, okay? Y is equal to a half, okay? It does the exact opposite. It goes down from on the left side, it increases, and on the right side of the y, it's an asymptote on the x-axis, okay? Does that make sense?
Yeah.
And finally, you have your sine wave, which we remember up, down, right? Cos, so this is, what have they represented? Oh, they've used the actual function. I've been using y, but they've been using f at x, g at x, h at x. That's fine, okay? I'm going to continue to use y just for simplicity's sake. Y, sine x. Y equals cos x. I don't know if you remember the rule for it, but instead of starting at the origin, it starts at 1. But then it does the exact same thing as the sine. And then finally, have you ever dealt with tangent?
Yeah.
Okay. Tangent x. Tangent x is actually set up just like the one above. It's an asymptote just like it, but it's several of them. So say it'll be an asymptote here, going up and down, and then another asymptote here, going up and down.
I haven't dealt with it too much.
Too much? Okay, you know what? I don't know how much you'll deal with this, so we'll keep tan off for now.
Okay.
Well, those are our signs. And these actually go in the negative round. I'm not sure why I didn't continue them. They go into the negative round. I know it's not very well drawn. That's the idea behind these functions, okay? So we have our functions there. What this one wants you to recognize is the many different ways functions can be drawn. So we have 1, 2, 3, 4, 5, 6, and then roughly trig is a function itself, 7. So there's like 7 different functions you're probably going to be dealing with in this course. Okay, so let's say we're talking about the linear function. That's the basic one. The skeleton model says y is equal to x. And we're going to talk about the different ways we can talk about things. So domain and range, that's our first characteristic, okay? Well, this actually goes, domain goes on the xy axis, there's arrows on both ends, forever. So essentially the domain is x, elements of all real numbers, okay?
Range is also like that.
Exactly, the range is y, element of real numbers, okay? So there's our domain and range for this one. X and y intercepts is another way we can do it. So our x-intercept just so happens to be when x is 0, what is y?
0.
Yeah. It just so happens on this base model function, it's the same. Now this can move, right?
Yeah.
Our x-intercept could be 2 and our y-intercept could be 3, like depending on slope and stuff like that. But in our base model, that's what we have for our x-y-intercept. They happen to be the same. 3, what's the third way? Continuality and discontinuality. This is continuous, this function. It goes on forever. Yeah. Now, discontinuality deals with when we start getting domains and ranges where we have exceptions to numbers, right? So this is
When do you have like a certain restriction, right?
Exactly. Continuous, okay? 4. Intervals of increase and decrease. Now, this is a constantly increasing if we're heading in the right. So when we're heading in a positive direction, so we're going to say positive direction, it increases. And if we head in a negative direction, this function decreases. Now, I know I only used symbols, but does that kind of make sense to you?
Of course.
Now, mostly what they do is intervals of increase and decrease. That's talking a lot more about, well, it talks about all of them, but it's very specific and important when we're talking about the trig functions because they increase from, say, 0 to 90 degrees, and then from 90 degrees to 180 it decreases, and then it increases again. That's the idea if we're heading in the positive direction. Okay. Symmetry. This is symmetrical whether we put it on the y or x axis. Okay. There's symmetry, so even and odd, and the end behavior.
What is that?
That deals with where a function has a start point. So the end behavior might change. Like maybe we're heading towards one direction, and then our end behavior is to fly up like an exponent. This end behavior is the continuous. It stays the exact same throughout it. So there's no difference in the end behavior of this function. Okay? Let's throw out another. Let's talk about quadratic. This is our quadratic function, and this is represented as y is equal to x squared. Okay? Now, with y equals x squared, our quadratic function, we can talk about our domain and range. Domain. What do you know about it? Yep. It's going to go on the x both ways forever. What about our range?
Unless 0 is less than x or equal to? Less or equal to. Wait, I need to write it down.
Okay, write it down. Yeah, so it's written just like that. It exists above 0, so y is greater than or equal to.
Does it really matter which way you write it?
No, if the 0's first, no, and it's really up to your teacher, Helly.
Oh,
It's just usually in the book they represent it the other way, but if you're fine reading it, it's fine.
Okay.
What are the characteristics? X-intercepts. Okay. Again, our x and our y-intercept are both at the origin. So when x is 0, it just so happens y is 0. Okay? But that could change. In fact, you could, with the quadratic, you can end up having 2 x-intercepts. Right? Continuality. This is continuous from left to right. And it continues upwards, but it does not head downwards in terms of, well, actually, sorry, if we're traveling from left to right, so say we're starting here, left to right, it's continuous and then it goes in this direction. Okay? And the same idea is continuous and it goes in this direction. So this is a continuous function. It's continuously touching,
Yeah.
So we have a continuous function. Does that make sense?
Yeah.
So it's continuous. 4. What's it? Intervals of increase and decrease. Okay, so essentially, if we're heading from left to right again, if we're going from left to right, say the function starts way up there, we're actually decreasing until we hit the y-intercept, and then we start to increase again. And the other idea is if we were starting on this side, going backwards, again, we're decreasing and then increasing. Okay. Don't think of it so much as starting at the origin. Think of it as we start at a point on the left or the right.
Oh, okay, so don't think at the origin.
You could, but normally in these types of questions, they'll ask you if you're in the negative realm heading in a positive direction, okay? So if we're in the negative realm heading in a positive direction, it decreases first before it starts to increase, right? If we're heading to the right. Now, if we're in the negative realm and they tell us to go even farther negative, well, then it's an increasing function when we're heading from here over, okay? So it depends on your starting point, okay? Symmetry, it's symmetrical on the y-axis. It's not symmetrical on the x-axis because we get an entirely different function. It's heading this way. So if I were to flip this, I end up with the exact same function that way. But I don't if I flip it on the x. Okay? And our end behavior, it continuously heads upwards at an increasing amount. It's constantly larger and larger every time. That makes sense?
Yeah.
Okay.